Okay, and one last thing I'd like to show this time is just some techniques for looking at polynomials using Matlab. Okay, suppose, for example, that I want to interpolate a function f of x. And here, oh, I don't know, let's just make up, maybe the sine of x is a good example. Or, well, better yet, let's do an exponential function. Okay. And then what I'll have to do next is pick some interpolating values for this function. So let me say that I'm going to interpolate at the integers between -2 and 2. Okay, that's my x data, and y will be my f data, which I can now get from just plugging into my function handle. Okay. And then what I can do next is construct an interpolation matrix. Okay, this is based on Lagrange interpolation. There's this built-in Matlab function called the Vandermonde Matrix. And let me show you what that looks like really quickly. Okay, and what this matrix is we've got ones along the first, or the rightmost row, column I should say. Okay, next is the x values of -2, -1, 0, 1, and 2, right here. In this middle column, this is the x's squared. So -2 squared becomes 4, -1 squared becomes 1, 0 squared, 1 squared, 2 squared. And can you see this pattern as it's going? This is -2 cubed. And this is -2 to the 4th, -1 cubed, and so forth. So what this does is naturally sets up evaluations of polynomials. In other words, if I had a constant term plus another constant times x, x squared, x cubed, x to the 4th, this Vandermonde matrix is looking at those polynomials at different x values, raised up to the 4th power, so that I have a square 5 by 5 matrix in this case. 5 points, it's going to be a 5 by 5 matrix. Well, suppose that we wanted to solve for coefficients of this polynomial that interpolates through the xy data points. Those coefficients, which I'll call a, are precisely given by v backslash y. And if I run this, and I have to be a little careful here, so let's go back. I would like this to be a column vector and not a row vector, so I'm going to put this prime here. And that'll change x and y into columns. And there, now this time when I run, here's my a vector. And this says that the polynomial fitting through these points on the exponential curve is going to be 1 plus this number x plus 0.49, etc., x squared, x cubed, and plus 0.049 x to the 4th. Okay. Now, we can also use some built-in Matlab functions to evaluate this polynomial. Let me go from the interval -3 to 3, and let's put in spacings of 0.01 here. So this will be roughly, 600 points between -3 and 3, and we would like to evaluate the polynomial at these points and store it as a 600 by 1 vector. So we'll call that P for polynomial. And the command is polyval, and you see it gives us a prompt here. The first of these vectors is the coefficient vector. That's A that we just received. And then now for the x, these are the evaluation points of the polynomial. That's t. Okay. And so this will produce P of t. And now, okay, so that's the previous graph. That's fine. Let me plot the following. Let's plot t versus, P versus t, the polynomial versus time, or the interpolation points, I should say, the evaluation points. And let's also plot the true function values, which is the exponential function at -3 to 3. And let's put this one in as a dotted red line. Okay, so we'll have a blue curve and a dashed red curve. Okay, and here is the fit, which from -2 to 2 is doing a great job because it's interpolating this exponential function at these 5 values. Pretty good fit in the middle. From 2 on to the right at 3, and from -2 to the left at -3, the polynomial will eventually fall off. In fact, if we extend this picture a little further, we'll see a big discrepancy between the polynomial and the true exponential function. Okay, so here that is. Right? Notice that in red, the exponential function will never ramp back up. It's monotone decreasing to the left. Polynomial is going to suddenly spout back up because, hey, that's a fourth order polynomial. It's only doing a good job of fitting the exponential curve in the vicinity of where it's interpolating from -2 to 2. Okay? And we can do this with other functions just by switching f of x. Okay, let me try instead, how about the cosine of x? And see, that's an interesting fit as well. Notice that the polynomial blows up, whereas cosine stays bounded between plus or minus 1 for all values of x in this interval. Okay, so that's probably enough to get started by looking at polynomial interpolation using MATLAB.